Hello, welcome back to this lecture series. Today we are going to be talking about weights and activations, and I'm very excited because weights and activations are really at the heart of a neural network. Because a lot of times we like to talk about neural networks learning. We'd like to talk about what a neural network is actually sort of doing to the data. And weights and activations are really at the heart of this because they determine the relationships between the inputs and the outputs. And they do a lot of things to do this. We're going to first talk about weights, and then we're going to talk about activations. So, in the introduction, I talked about weights as visually as that line between the neuron and the output neuron in the next layer. So I've done a little bit of a close-up here, and I've actually included the numeric representations of all those weights. And I also told you that the relationship between a weight and a neuron could be represented numerically by the operation of multiplication, by scalar multiplication. So I've included all of the numbers for the neurons and all of the numbers for the weights. So the first thing we're going to do is just multiply and get values for all of these. So we'll do 1 times 2, which is equal to 2. This is going to be 6. This will be -3. This will be 0. This will be -12. And this will be 20. So if you're following, this is just a result of the multiplication between the weights and the neurons in the previous layer. So if you want to think about weights in a more conceptual level, you can think about weights as the amount of say a neuron has when it comes to the emphasis it will have on its output neuron. So in this example, -2 has the most say with a weight of 6, and 0 has the least say with a weight of 0.5. 0 is a bit of a different case because it wouldn't really matter how much we multiply by. But anyways, that is all that you have to know about weights. You're just multiplying scalars by another scalar. And we're actually going to talk about how we can do this in a faster way through vectors in just a second. But before we do that, we have to talk about what an activation is. Now, an activation is what happens after we multiply the weights and the neurons. So after we multiply the weights by the neurons, and we want to be able to add all of these outputs together. So we're going to do that. We're going to add 2 plus 6 plus -3 plus 0 plus -12 plus 20. And I believe this output will be 13. So this output is going to be 13. So if we imagine that our activation is happening right here before we get our output, what we've done is just added everything from these weights together. And then what we're going to do once we have that is, this is a bit of a throwback to the last video, we're going to map to the sigmoid. And if we remember what happens when we map to the sigmoid, we can take in any input we want from -infinity to +infinity, and we'll get an output between 0 and 1. So if we go back to our sigmoid, essentially what we have, if we continued this, is at 13, we would be getting some value up here. And now feel free to do this if you want, because in the code last time, I had you make a sigmoid mapper. So you can just plug 13 into your sigmoid, and that's going to give you the output right here. So this output is just going to be the sigmoid of 13. And there's a quicker way to do this. But before we do that, we have to talk about one last feature, which is bias. Now, sometimes you want a neuron to output values at a consistently higher or consistently lower value. And all we need to do to solve this is add or subtract a constant value, which is known as a bias, to the sum before we map to our sigmoid. So if we write our bias in red, we can just say this bias is, let's say we wanted to add 10 to our... Before I go though, I want to talk about weights and the sort of multiplication operation, as well as the activation function, when it actually comes to mathematically doing this in a neural network. Because very fascinatingly, it all happens in one step. And the reason it all happens in one step is because the machinery that we run neural networks on, graphics cards and whatnot, is very good at matrix multiplication. And this is what really made the neural network possible. So all we have to do for that is first represent all of these neurons in this layer as one matrix, or one vector, pardon me. So we just need to write 1, 2, 3, 0, -2, and -5. So that's simple enough. And then we write our weights as another vector. I'll do it in a different color. 2, 3, -1, 0.5, 6, -4. So there is our two vectors. And all we have to do this operation, this first operation right here, in our activation, is just take a dot product. Because a dot product is simply going to multiply these values together and then add them. So the result of this dot product is going to be 2 plus 6 plus -3 plus 0 plus -12 plus 20. Which, if that looks familiar, it should, because that is just our first step in our activation function. Now, all we need to do is just wrap this. Here, I'll move this over so we have a little more room. Wrap this. Sorry. We just have to wrap this in our sigmoid function. So that's all we have to do if we want to do the outputs all in one step. And if we wanted to add a bias, we could just add that in there. So if I were to write like a line of code, we're going to do this at the very end, but if I were to write a line of code to represent everything that we've learned today, it would just be simply, let's say we have a vector representing our neurons and a vector representing our weights. I would just say, let's say we have a dot, which will represent our dot product. I'll just do the dot of the inputs and the weights. Plus bias. And all of that gets put into the sigmoid. Very simple. It's all just one function. It's very elegant, and it works very well. So that's it. That's weights, activations, and biases. So as an activity, before you go, I want you to imagine something. So imagine that we all have a bunch of laser pointers. They're all pointing at a light sensor. So after a certain threshold, the light sensor is going to play a little noise. So we have a bunch of laser pointers. They're all pointing at this light sensor. This light sensor has a certain threshold, and then it's going to play a little noise. So your job is to write the code, which is going to take in the brightness of the laser pointers and figure out if the noise is being played. So I want you to use the sigmoid function, the last activity, to determine the threshold, and do your math with vectors and dot products like I just showed you. And as a bonus, try to fiddle with the threshold through the bias. And I'm going to write all this in the Colab notebook written below, and I will see you all in the next one. And in the next one, I hope to talk to you about confidence, error, and cost. And there we're going to get into a bit of the learning aspect of a neural network. So thank you.